So welcome back to the lecture 12. Today it is 8th December 2020. So we have seen that in our last class, I am just doing a summary. We have seen the stability, and also we have seen how to draw the stability circles. Also we have defined few things which is unconditionally stable, conditionally stable, and we have checked something called k delta test and mu test. All those equations we have seen. So based on that today we will actually solve some problem. So let's start with the first problem. So suppose we have been given a transistor whose S11 value is 0869 angle minus 159 degree. Then S12 value which is 0.031 angle minus 9 degree. S21 is equal to 4.250 angle 61 degree. S22 is 0.507 angle minus 170 degree. So these all is measured in a 50 ohm reference impedance, and also at f equal to, let's say, 1.9 gigahertz it was measured. Now you see things, so this is the transistor. So if you see the transistors, this is the transistors block. So I call it as a gain stage. I call these transistors as a gain stage. You can see that here this to this propagation, port 1 to 2 again, which is high, 4.2 magnitude, whereas if we check the backward propagation, which is S12 magnitude, which is quite low, 0.031. Now I will the question asked was, what is the determine the stability and plot the stability circles. And plot the stability circles. So first, to check the stability we have to use the k delta test. So for the first part we have to do the k delta test. So initially, to start with, I need the determinant value of mod delta. So mod delta is S11 S22 minus S12 S21, which is 0.336. let's say I calculated. So actually this is of the form R1 angle theta 1, R2 angle theta 2. So R1 R2 angle theta 1 plus theta 2, like that you have to calculate. Similar way it will be like that, and from that again you have to take the deletion, and then you have to take the magnitude. It's a simple complex algebra, using complex algebra. So I calculated the mod delta value, which is 0.336. Now the value of k, if I have to calculate, it will be 1 minus mod of S11 square minus mod of S22 square plus mod of delta square divided by 2 of S12 S21. So this value, it will be 0.383. Now we all know that for unconditionally stable device, my k should be greater than 1 and my mod delta, it should be less than 1. In our case, mod delta which was less than 1, but k is not equal to greater than 1. The value of k is 0.383. Hence the conclusion is the device is not stable. Okay, Now I have to draw the stability circle. So I can check the calculate the value of mu also separately. If you see the value of mu, it will come around 0.678, which is not equal to greater than 1. So again the conclusion is the device is unstable. So the any of the route you can go, it will tell you that the device is not stable. Now to draw the stability circles, let's say I want to interested the output stability circle. Let's say I want to draw the output stability circle. So to draw the output stability circle, what I'll do, I need to use the formula CL, which is S22 minus delta of S11 star whole star divided by mod of S22 square minus mod of delta square. So I calculated these values is coming 1.59 angle 132 degree. Similar way RL if I calculate, which is my last lecture, divided by mod S22 square minus of mod delta square, which is 0.915. So this is my output stability circle. Now to draw it, I will go back to my Smith chart plot. So let's say my Smith chart plot, it looks like this. So let's say it is my tau r, j tau I, okay. So this is the circle which I draw, which is r equal to 1 circle. Now whenever you will draw it, you will must notice that in the Z Smith chart there is a coordinate which marks as reflection coefficient mod tau, and the values are 0.1, 0.2, like that it is increasing up to 1. Now I have to find it out, the complex value 1.59 angle 132 degree in the Smith chart. Obviously the Smith chart inside it is magnitude 1, so I have to go till 1.59. So then what I'll do, I will have to take a take a 132 degree first the angle. So let me take a 132 degree. So I will do 132 degree. So let's say this is my 132 degree. So I will come this side, and let's say this is my 132 degree. So from this side to this side I will draw this straight line. Now from that straight line I need to go 1.59. So I know from here to here it is 1, and then extra 0.5 I have to take from here to here. So this I have to take it from 0.59. So that will come 1 plus, let's say from here to here it is magnitude 0.59, and here comes my center. So I am plotting this as my center. Now so this is my center. Now the radius is 0.95. So the radius, let me take in some other color. So let's say the radius is coming around 0.915. Let's say this is my radius. I am writing it as RL. So that radius is 0.915. So that means this is 0.59. So it will cross the value of 0.59, that extended part. So obviously whenever I will take the center and the radius 0.915, it will cut my Z Smith chart, and it will extend inside the Z Smith chart, and then it will follow its circular locus. So the 0.915, if I from putting the center here, from here if I see 0.915, let's say it will come along this much. So then this much is nothing but my here to here. Now with that if I draw the circle, so this is my circle which I draw, and this I am calling it as a output stability circle. So it is my output stability circle. Now again, to choose the stability, so that means this is the point where my mod tau in equal to 1. Now one side of that stability circle obviously will have mod tau in equal to less than 1, and the other side is mod tau in greater than 1. So the same way we decided in our last lecture, this time also we will do. We will put a special point, and the special point is nothing but your load reflection coefficient 0, tau L 0. And I know that this tau L 0 is the Smith chart origin. So like my last class, I had to take, I will just repeat that fact. So tau in was S11, S21, S12 tau L divided by 1 minus S22 tau L. Probably this was my formula. And tau L I have put it as 0. Now depends on the value of S11. I will go there and I will check what is my value of S11. I check it is less than 1. So when it is less than 1, obviously then my tau L equal to 0, which is origin, which will fall in less than 1 means stable zone. So then the zone which is intersected with the green color output stability is nothing but my output, nothing but my oscillatory zone, or nothing but my zone which is unstable. So I will put it in a different color. So this zone is my unstable. So I will draw that this is my unstable. So I will write it unstable zone. So this is mod of, I should say my mod of tau in greater than 1, and the zone which is coming inside this, I will put it in blue color. This zone, this is the zone which is this entire zone. So let me draw it in a dot in this manner. This is the zone which is marked by these small solid balls. This entire zone is mod tau in, which is less than 1 and is termed as stable zone. So the point of learning is that how I took my radius and the center to draw the green color output stability circle. So then one might draw the value of the input stability circle in the same way that I am not showing it here. So the same way, just he has to take it and you have to calculate the value. It might happen that it may fall outside these things. So if it is falling outside this thing, in that case it is the case for unconditionally stable. Now I will, so that input stability circle draw, you can take it as assignment. So the output stability circle I show, the input stability circle you can draw on your own. Now I will talk about one important problem. Let's say I want to discuss, let's say, so one case I want to discuss. So I am writing, I want to discuss the stability achievement using the resistive element. So what does that mean? I am actually meaning. So suppose you have for a particular case of transistors, you draw the input and output stability circle. Let's say I have drawn this is my tau R, this is my J tau I, this is my these values. Now let's say for a particular case I draw that my output stability circle. So I have been given some S parameter value, and from that let's say I have my S parameter value. From that I can draw the input stability and output stability circle. Output stability circle. So I will take the case again. So let's say after drawing the output stability circle or input stability circle, let me take maybe let's say the output stability circle is coming like this. Let's say this is my output stability circle. I'm discussing a case, in any general case. In that general case, this is my output stability circle. This is my output stability circle, and the value of S11 is such that let's say it is less than 1. So in that case, again I can call that my unstable region is like this. Now this means, this is the region means it is unstable. Now at this stage I cannot design any amplifier, since if I design, then any load that I will choose from this region will lead to a oscillatory position, will lead to a unstable amplifier. To eradicate that or to remove that, what I will do, I will always want so that this situation can never occur and my circles, so that my circles make fall apart. So how I want my circle to look like? One circle should be look like this, that I already have drawn, and I always want so that my blue circle, which is nothing but my output stability circle, can be pushed outside the Smith chart. So in better way, if I can fall it in this fashion, then it is very good, because this is the case where unconditional stability I can achieve and I can get rid of this yellow color region. Now to do that, I need to have a connection of a resistance, and that's why I brought into the resistive element effect into it. Now how the resistive element is helping me to do it? See, in this output stability circle, whenever it is there, I know that my resistance is here, it is a Z Smith chart, so it is 0 here and it is infinity here. Now I can always see that my constant resistance circles, how they are moving. I can see that my constant resistance circle, that it is moving, they will move in these fashions. Now one of the constant resistance circles, let's say I was drawing it in a black color, one of the constant resistance circle, it will be going dot color and it will be going like that. So one constant resistance circle at point A, it will be a tangent with the output stability circle. So that is marked in dot color. Now how to determine what is the value of it? So the constant value, if I have to determine, then I have to see the connections or intersections with the tau real axis, that is the point. So this point is A, and the point which is here, let's say this point is C. The point C is the value of the constant resistance. Let's say this value, how much it is coming. So this is abruptly drawn, but since it is coming here, let's say if it is 1 normalized, let's say it is coming 1.2. So I am taking the point C value and I marked it, and the marked I am getting it from the real axis where it is cutting from the Z Smith chart. I noted the value which is normalized 1.2. Now I will denormalize it. Denormalize. So how I will denormalize it? So the value that I have got, which is Z0 equal to 1.2. So that means Z by Z bar equal to 1.2. So Z equal to 1.2 into Z0. So it will be 12 by 10 into 50, 60 ohm. Now this 60 ohm resistance is important. In what sense? It is important, because this impedance, if I can connect it, this impedance, if I connect it with my output side, this system with these resistors will make this to happen. It will every time this whatever resistance it was adding, this is the touch point, is from this origin is actually the highest touch point, and from that, the moment you are adding an extra 60 ohm resistance, it is actually pushing all the locus corresponding to this falling inside, that is pushing away that circle outside the Z Smith chart. So that is why then this circle will be putting outside the Z Smith chart, and there will be no intersection in between them, lead to an unconditionally stable case. In the similar way, what I'll do, so I have connected it in the series. Why? Because I have point of tangent was marked from a constant resistance circle. Now there will be a one more case of this. So the same figure I will draw. Let's say I am drawing the second case, stability circle. So let's say what I will do again. So that is maybe one series configuration. Now one more case it will happen, so let me draw it here. So again the same way I'll draw. So this is my tau r, this is my j tau I. Again I will draw the output stability circle. The output stability circle was coming here. The same example I am taking. Last time we have made a tangent with the constant resistance circle. Now the same thing I am showing it in the ZY Smith chart. So I am marking it as case 2. So the case 2 ZY Smith chart. So what it will happen, my constant conductance values are here. As far as constant conductance value, it is infinity, and let's say it is 0. So then obviously one of the constant conductance point, it will be again tangent, and then it will be like that. Let's say that value, since it is close to 0, this point I am marking it as this time point AA. So the point AA, what is the constant? What is the constant conductance? For that I need to check the point which is cutting with the real axis, real tower axis, which is point CC. So the point CC value I have to note. Let's say since it is close to 0, let me take it as, let's say, 0.1. So then this is normalized, so I have to denormalize it. So if I have to denormalize it, that means y bar equal to 0.1, y by y0 equal to 0.1, then it will be 0.1 into y naught, 0.1 by z naught, 0.1 by 50, and if I calculate it, it's going to come around, how much? It's going to come, I think, around 2 millisiemens. It's going to come around 2 millisiemens, or if I revert it, it will goes to 500 ohm. So that means, considering these effects with the constant conductance circle, this I got it from case 1, and from case 2 I can use these transistors with a parallel 500 ohm resistance, and I can make the systems again work as a unconditionally stable. So that is what the importance of connecting the resistance at the suitable place. And you might have noticed in the lab that you have done, sometimes we add a small resistance, and that is nothing but a stabilizing network. Sometimes we add it a small RC parallel connections in series as well as in parallel. It all we do so that we can drive the output or input stability circle away from the Z Smith chart, and we do not get any such intersected region, so that our total load we can access as a freely, and we don't have to bother about the stability, so that we can make the transistors unconditionally stable from the potentially unstable case. So I have done this thing actually with the case of output side, because I took the calculations, I took all the values from output stability circle. The same thing if someone does it starting from the input stability circle, in that case he has to connect all the resistive elements in the same way, but he has to connect it in the input side. So in the input side I am not showing, you will do it on your own, and you can see that the technique is exactly similar. I do it for output stability circle, and input stability circle for a particular problem you can take and you can add that and you can verify it in your ADS. So till then, goodbye. We have any doubts regarding this, you go through, and then we will discuss in a live sessions. So I have to mention it. So this is like a output stability circle. So it is output stability circle. So I will put it as CLRL. If someone does this problem with input stability, he would connect the resistance in an input side. So that is an assignment. So I am writing it. My assignment is do the similar study for a particular example. Suppose the example, you can take whatever I have taken here. So you can take this gallium nitride HEMT process. So these values you can take, and you can take this analysis you can do, and you can show that to the similar stability for a particular in the input side, and comment on the value of the resistor. So I am just writing comment on the value of the resistors. If you find the values from the input stability circle, connect it at the input side. I have connected all those things in the output side because I have found all those values from the output stability circle. So I will mention it. It is also a very important point. The point is that I have connected all these at the output, since we have got it from the range of towel stability or output stability. If you do it from the input side, you obviously have to connect it the input side. So that's goodbye till then. We will meet in some of the classes, live classes, and we'll discuss further. So till then, it is goodbye. Thank you.